Okay, I think I'll get started. Uh, this week, we're moving on to the third of our modules, which is a much longer module. We sort of completed that first week where we looked at Python programming, Python packages. That second week where we looked at data handling, data visualization. Now we're going to look at ordinary differential equations, solving ordinary differential equations. We're going to look at numerical methods for solving ordinary differential equations. Our focus is going to be first order ordinary differential equations and second order ordinary differential equations. I think almost all ordinary differential equations in physics are either first order or they're second order. I think to get a third order in physics is a very rare thing. Over the next few weeks, then we'll explore some problems using numerical solutions of ordinary differential equations that go way beyond what you can do with sort of pen and paper and analytical work. So we're going to look today at falling bodies. It's sort of an introductory example for us. We'll look over the next week's pendulum motion and other periodic motion as more complex example of ordinary differential equations. So that's the plan. Okay. So we start talking about falling bodies. We've already talked about falling bodies in our very first class where we solved in Python the arithmetic of falling bodies, i.e. predicting the distance fallen or the time taken for a falling body based on Galileo's free fall law, that in absence of atmosphere, in absence of air resistance, all bodies fall with the same constant acceleration. So that law we can write as ordinary differential equations for the position as a function of time or the velocity as a function of time of the falling body. And the equations we used in that very first class were equations that came from the solutions of these ordinary differential equations for velocity and position as a function of time. And so these are two equations here. Top one's first order ordinary differential equation. Second one's second order differential equation. These are the equations that we'll work on today as examples and illustrations. So sometimes I'll use this notation on the left-hand side. So I'll write out the differential, say the velocity is dv dt. Sometimes I'll use this prime notation just to make it more compact. But anyway, in free fall, the rate of change of the velocity is determined by the acceleration of gravity. Is a constant. And so we can express that here. My minus sign here is just that I've chosen to think of the positive direction as the upwards direction, and the downwards of acceleration of gravity I've indicated as minus g. Downstairs here, we got a second order differential equation. So I'm either denoted in it here with this second order differential of the position, or with this prime notation, double prime notation for the differential of the position. And again, this is simply saying that the rate of change of the position is determined by the acceleration of gravity. And so we'll go ahead and solve this first order and then this second order differential equation numerically. And we're going to do it using what's called Euler's method, and that will give us the velocity and the position as a function of time. So one of the nice things about solving numerically rather than solving analytically is when you solve numerically, it's very easy to extend your solution to more complicated situations, like when there's air resistance, when there's a drag force. And so we'll be able to easily extend our solutions to include air resistance, to include drag force. That would be more difficult to do analytically. In this case, not impossible to do it analytically, but it's more complicated to do it analytically. So if an object is falling through, say, air, or maybe an object is falling through water or some other viscous fluid, then in general, there's a force that resists the motion of the object. There's what we call a drag force. So FD here is our symbol for the drag force. So generally, that drag force is opposite the direction of motion. And generally, that drag force is a function of the velocity of the falling object. But generally, it's quite a complicated dependence on the object, its motion, the fluid, its properties. There are two sort of important cases, and I've listed them here. So in some circumstances, the situations are that the drag force is approximately a linear drag force. It depends linearly on the velocity. It grows linearly with the velocity. And often we write it in this form here. This parameter B is just a coefficient that is determined by properties of the falling object, properties of the fluid is falling in. And then sometimes there's another limiting case that's important, where you get a quadratic drag force. That's where the drag force is in proportion to the square of the velocity. And again, there's a coefficient, here it's C, that characterizes the properties of the falling object and the properties of the fluid that it's falling through. The minus sign, just to be clear here, the minus signs here are just kind of reminders that the drag forces are opposite the direction of motion. So they're just reminders of that. So in general, the calculation of the coefficients, the B and the C for the linear and the quadratic drag forces are quite complicated. In a particular case where you're dropping spheres or you've got falling spheres, it's somewhat simpler to calculate those coefficients. So in that case of a sphere of some diameter, some mass, falling through air at standard temperature and pressure, then there's these little expressions here. So this one for the coefficient with the linear drag force, and this one over here on the right for the coefficient for the quadratic drag force. And the D here is the diameter of the falling object. And the numbers are just numbers evaluated for objects falling through air at standard temperature and pressure. So I mentioned that under certain circumstances, one or other of those linear quadratic drag forces can dominate. So famous examples are if you throw a baseball, drop a baseball, it's normally the quadratic drag force that's dominating in air. A example of a linear drag force dominating, you've probably heard of the Millikan oil drop experiment that was used to measure the electrical charge of individual electrons. So in that, you're dropping really, really tiny diameter, really light oil drops. There is linear drag force that dominates. So baseball and Millikan oil drop are kind of classic examples of where you've got linear or quadratic drag forces. So we'll extend our solutions to the differential equations for the position and the velocity of a free-falling body to incorporate these drag forces. And I've just shown you on this overhead an example of that. So here's a here's a first order differential equation for the velocity. It tells us the rate of change of the velocity, and we've extended it to incorporate the deceleration due to the drag force. And this is a quadratic drag force. This is the coefficient of the quadratic drag force. And this is the mass of the baseball, say. And then here's the second order differential equation for the position as a function of time. Again, we've extended it. Here's the free fall acceleration of gravity. And then this second term here is the deceleration resulting from this quadratic drag force. And so we'll solve both of these with the same code, basically, that we solved the free fall cases.